Welcome back to The Explainer. Today, we're going to dig into a fundamental question in computing. How does the code we write, the stuff that looks kind of like English, get turned into the raw electricity that actually makes a computer do stuff? We're going to climb the ladder of abstraction, so let's get to it. So last time, we saw that assembly was a huge leap forward from just punching in ones and zeros. But, let's be real. It's still super tedious to write, it's easy to make mistakes, and your code is totally stuck to one specific type of hardware. Surely we can do better than that, right? And here is that better way. The difference is just night and day. On the left, you've got assembly, all those little painstaking steps. And on the right, a high-level language. It's the difference between telling someone how to get to the store by listing every single footstep versus just saying, go to the store. One is for the machine, and the other is for us humans. Okay, so that's a pretty huge gap, right? How do we possibly get from our simple idea on the right to the machine's complex reality on the left? Well, the answer is a really, really clever piece of software called the compiler. Think of the compiler as your own personal expert translator. It takes one language, the one we think and problem solve in, and it systematically converts it into a completely different language, the one the processor actually speaks. And the compiler is exactly what makes these high-level languages so powerful. We can use math that looks just like the math we learned in school. We can write way less code to get a lot more done. And maybe most importantly, we get portability. That means the same code can be compiled to run on your phone, on my laptop, or on some massive supercomputer. It's a game changer. Now, this right here highlights a really key difference. An assembler, you'll remember, does a pretty simple one-to-one swap. One assembly command equals one machine instruction. A compiler, though, is way smarter. It does a one-to-many translation. It can take a single, powerful line of our code and expand it into 10, 20, maybe even more low-level instructions that the machine needs to get the job done. So, how does this magic translator actually work? Well, it starts with something called syntax analysis, or parsing. You can think of it like your old grammar teacher diagramming a sentence. The compiler reads your code and breaks it all down, figuring out the structure, the relationships between the parts, and what you're actually trying to do. So, once the compiler understands the grammar of your program, it starts translating. But here's the cool part. It doesn't usually go straight to the final machine code. Instead, it generates an intermediate language, something often called VM code. Think of it as a generic, middle ground version of your program. It's not human language, but it's also not tied to any specific hardware yet. This makes it way easier to adapt later on. Now, we don't just write our software as one giant single file. We break it up into smaller, reusable pieces called functions. And this is great for staying organized, but it creates a new puzzle for the compiler. How in the world do you keep track of which function called which and where to go back to? The solution is a really elegant idea called the stack. And that elegant idea is called the stack. The easiest way to think about it is like a stack of plates at a buffet. You can only put a new plate on the top, and you can only take a plate off the top. That last in, first out rule is the simple, brilliant trick that keeps all those function calls from turning into total chaos. And here we can see that stack of plates in action. So our main program is running, it calls a function, boom, a new frame with all that function's info gets pushed onto the top of the stack. The function does its thing, finishes up, and then pop, its frame is taken off the top. This simple push and pop system guarantees that the program always knows exactly where it was and where to go next. It's a beautiful solution to a really complex problem. All right, so we've got our compiled code. We have a system to manage all our functions. We are so close. But there's one final, absolutely massive layer of software that makes modern computing possible. It's the big boss, the program that sits between all our applications and the raw hardware, the operating system. The operating system, or OS, is basically the conductor of the entire orchestra. It's this huge, sprawling program, and its whole job is to manage everything, making sure the hardware and all the other software on your machine can work together without causing a disaster. So the OS really has two main gigs, and they're both critical. First, it's the protector. It's like a bodyguard for your hardware, making sure that one buggy or malicious program can't just crash your entire computer. And second, it's the helper. It's like a concierge that handles all the complicated, messy, low-level tasks for your applications so they don't have to. And the way the OS does all this is through the power of abstraction. It creates a bunch of really useful illusions for our programs. For example, it gives every single application the illusion that it has the whole CPU to itself, even when you've got dozens of things running at once. It gives each program its own private safe memory space. It makes talking to your keyboard or printer super simple. The OS basically creates a nice, safe, simplified bubble for our software to live in. So there you have it. We've climbed all the way up from the physical hardware to our high-level thoughts. Now, let's just take a moment, stand at the top of this ladder, and look down at the entire software hierarchy we've just put together. And this is it. This is the whole epic journey. Your code, the stuff you actually write, starts at the top. The compiler turns it into that intermediate VM code. Then a VM translator turns that into assembly. Then the assembler finally turns that into the pure binary that the hardware understands. And the whole time, watching over everything, helping out, and keeping things safe is the operating system. And all of this brings us to what is, arguably, the most important single concept in all of computer science, the Instruction Set Architecture, or ISA. This is the fundamental contract. It's the sacred meeting point between the world of software and the world of hardware. It is the language that allows our ideas to become physical actions. You know, every single layer we've looked at today was invented to solve a problem, to make computers more powerful, more accessible, more reliable. This whole amazing structure is just a monument to human ingenuity, which, of course, makes you wonder, what are the big, seemingly impossible problems we're facing today, and what brilliant new layer of abstraction are we going to invent to solve them?